What about and you can see your soldier crest.
A what?
Welcome to this week's
Soldier
CSAM meeting, and I would like to introduce Pablo, who's talking on what the bees know.
Thank you. So, thank you guys for just inviting me. I just joined, just started to join the group, and I don't know if coincidentally now I was chosen to give this talk for you guys. And I'm not going to specifically just talk about my work, but some ideas that we had, and some things that we think, and some things that motivate our work, and that are broad and can be more useful for you guys. And so I'm a third-year candidate student here in the applied physics program, and I work with Csaaw in the chemical engineering department, and I will be talking about shapes pretty much, and how shapes can be used in chemical engineering, and also are found in nature and can motivate some of these things. This title, What the Bees Know and What They Do Not Know, it comes from a very interesting paper by French thought that studies pretty much this idea of the honeycomb and things that I'm going to be talking about today. So basically, the contents of my talk is what the bees know, what they don't know. And it's basically the division I'm making. And for all of us, it's probably not a surprise the kind of symmetries that we can find in nature. And when you look at things that are present in nature, you just find these amazing things that are completely symmetric and very mathematical, like those flowers with exactly 8 leaves here that are crossing each other, or those fivefold symmetry. And several times you can think in those things in mathematical form, and you can detect mathematical laws in all those, in several different things that are present in nature. And that was something that made Darcy Thompson in 1917 to think there is something here. He was a mathematician and a biologist, and he wrote this big book, over 1,000 pages, where he's basically talking about this idea that math is presented everywhere in biology. And if you just think in terms of Darwin evolution theory, that you can think about that if you can find a reason why they are symmetric. But he says you don't need Darwin theory, you don't need to think why those things are symmetric according to Darwin's law, because it should just come from laws of physics. Laws of physics are symmetric, and if you see something that is pretty symmetric, like the things I'm showing here, like a ice crystal that grows with 6-fold symmetry, or the ways that shells grow with a logarithmic kind of growth, this is mathematical, and this comes from the fact that the laws of physics are mathematical.
What is this fruit? What is that fruit?
I don't remember the name in English.
Pepper?
Yep. And although these kind of things you can see in Da Vinci's work, where he makes all those symmetries in his sketches, and also in works by Turing. And at first thought, you cannot see the how controversial that actually is. But I don't know if we have biologists in the group. We have a few. Because this is something that, at least from reading from the books that we see, I'm going to mention at the end, but what I've been reading is that these ideas that biology can be predictive, you can use the laws of physics to detect how an animal or a given organism would evolve just by laws of physics, is very controversial. There is a lot of controversy. And one example of that is, if you look at this horny dude over here, has
wow.
The basic idea is that in the same way that we solve some problems in physics, where you have this metallic strip, and you have 2 different metallic parts, and when you make hot, it bends because of the way it grows is different for each one of the metals. And that's basically the idea that he says that governs the growth of a horn would be you have 2 different parts that are growing different rates, and that is going to you can calculate exactly this curvature based in the way it grows. And the basic idea of Dorsey Thompson is that this is all physics, and biology is using the laws of physics to make something that biology needs. In this case, the horn. There are like modern views for that. You can look in Geoffrey's YouTube page. He has this nice video on YouTube where he talks about complexity, and he talks about those ideas as nature is trying to maximize something. In this case, there is a need for a horn, and nature is just trying to maximize this function of need for a horn. And if you have two different islands, and he says this example in his video, and if in those two islands you have, in one of the islands you have an animal that grows one horn that's straight, and the other island you have like two horns, biologists that are just following Darwin, they would say, oh, in this island, one horn was better for some reason, while in the other island, the ones with two horns won because it was better for another reason of the environment. And he says, you don't need to think about that. That is, you don't have to, every single thing, you have to find a reason for that. Nature is trying to maximize this function of I need a horn in this case, and you can have several possibilities on how to do that. And in one place you can have one animal that found a way to make a horn that's straight, and the other way you can find with two horns. In another place you can find a horn that is curved. And this is very interesting because you can think about predictability, predicting where biology is going, given specific rules. So I come to the honeycomb problem that I'm going to be talking today. And of course, this is pretty old. It's probably the first example where people found symmetry in nature and stop and say, hey, this is actually pretty symmetric. Something is going on here. And probably the first place where we have written register of that is in Pablo of Alexandria, great Daphne. And what he said is basically that...
Doesn't look Greek.
Huh?
Doesn't look Greek.
He is, isn't it?
That sounds Latin.
Well, roughly at that time, Alexandria, the ruling class was Greek because it came from Alexander. It was one of three of Alexander's generals. So Cleopatra was Greek, by the way.
That's what the Wikipedia says.
Everyone important.
So what he says is basically that if you have a two-dimensional area and you want to divide that in equal in different sections of also equal area, and what's the one that you can choose that has the minimal amount of wall length here that can tile the space? And he just makes this conjecture that hexagonal is the best from all the possible ways that you can imagine doing that. But no proof was done there, and it's basically a conjecture. And of course, Darwin got pretty happy about that, and he mentions it in his book as being the perfect example of economy of labor and wax. That I really tried to find a picture of Darwin like smiling, but I couldn't find it. It's just impossible, so I just put his head that he was actually pretty happy with that. And he mentions that if you have a bee that is constructing a hexagonal house for the honey, what happens is that this bee is going to go and construct the house, and it can more quickly come back to get honey than some other bee that's making anything other than hexagonal array, just because this one is way faster to construct because it uses less material to construct the wall. And it seems reasonable, it seems in agreement with his theory. And what Dorsey Thompson would say is that why you complicate it so much? Why you have to go and try to find a reason for every single thing that you see, where we know that if you take a bunch of bubbles and they are in the same size, or imagine the M&Ms are spherical, and you just try to put them together and you compress and try to find the best way of them to pack, they are going to make a hexagonal array. So if you take a bunch of bees and each one of them are making, each bee is making a bubble where they are going to put the honey, just by packing constraints, they are going to form a hexagonal array. And this hexagonal array is going to pack exactly like that, and it's going to form those walls just because the temperature of the bees there is enough to make the walls elastic, or you can move, and it's going to form something like that. So this is his argument, and this is his argument in the whole 1,000 pages of his book, is that every single thing he's going to use a different example to say, you don't need to go and think about Darwin's theory all the time. Physics can tell you about why some things are in this way.
So according to Thompson, why is it that squares are less optimal than like hexagons?
So in his case, if you try to
You can pack squares.
Well, so what he's saying is that you make a bubble, and because if you try to make a bubble is going to be spherical, just because of the laws of physics. The bubble is spherical. And now every bee is making a bubble, and they are pushing the bubbles together, and they pack hexagonally because it's the best way of packing spheres is in a hexagon array. To pack as a square is worse.
So they pack hexagonally, and then because they squeeze, they deform slightly, so they form these hexagons.
But his point is the bees are not choosing what to form. They are making circle bubbles that are pretty much of the same size.
So no, but right. So there's so physics operates according to energy minimization to a large degree. Right. So what Darwin is really saying is that there's a minimum number of resources being consumed. So maybe there's a correspondence between the underlying assumptions of Darwin and those of Thompson.
What I got from Thompson's point of view in his book was Darwin's evolution operates, but nature gives the number of available possibilities that it can operate. So he's saying you would never see. This is hexagonal because you would never see a square because a square is not stable. So it's not that the hexagonal is better and the bees are winning. It's because there is just no way of making a square. Because if you try to put bubbles in a square and you just give a little bump, it's going to arrange hexagonally because it's not stable. You see the little difference? It's a little difference, but it makes.
I do
agree, though. I think there is a corollary because even though physics, and I think you're expressing this yourself, physics provides all the possible solutions, and then, say, biological evolution will slowly converge to one, and then once it gets into this proper trajectory, it'll just fall into that local minima via the laws of physics.
But I don't see, so I don't understand, in this particular example, I don't see what you're saying.
Maybe not here.
Because, okay.
But his basic point is that, so what several of those books said, and that's why I asked if there are biologists here, because I've been seeing over and over that most biologists don't agree that you can actually have equations that dictate what is the evolution going to act. And this guy and others are going to just agree that, no, you can't think, we are probably just not finding, but there are equations that are going to dictate.
I mean, it seems like essentially you're saying the genotype-phenotype map is defined in a different location. You're saying that the genotype is determining the behavior of the bees, which is then going to be subject to the You're just saying that basically bees don't have the phenotypic ability to sort of decide whether the square versus isomorph.
Darwin never said that these things were decided in evolution.
Right. It's more like a modern, I don't know if it's a modern view, but maybe he was just going against everyone, explaining everything using just now, but you can just think that this guy has one horn because, it's better for this place to have one horn. But no, it's not necessarily this place is better to have one horn. It's just that nature followed this minimal, found this local minima.
But one problem with Jeff's point, he only had one type of animal on each island. You've got to have competition. You don't have that after the selection. So that's very different from the Galapagos, where there are lots of different variations on the finches.
You're talking about the here when you have local minimum.
You got to have to get something out of that. One question too, Pablo. I understand the squeezing argument, but what determines what the radius is?
So he doesn't say that, but in like modern things, it's basically the way, if it's honey, they have like a amount of honey that they can carry, and basically every bee is the same size. So it's like a monodisperse kind of thing.
Good.
It's kind of similar.
Yeah, it seems like
It seems like the situation here would be something
very
like
small variation.
you don't, you could have natural selection on thickness of walls or size of the radii, these things, but you won't get any selective pressure not to be building squares because you just kind of can't build squares. So
Yes.
one can come up.
Right.
Yeah.
So I don't know about how modern views are about these, of including the selective pressure in Darwin's model, but for sure in 1917 that wasn't the case. So that was the point of Thomson.
Yeah, I mean it's useful because at least he elucidated. Think there wasn't a bunch of like a polygon battle going on.
Yes,
This
Scientists,
is what happened.
that's
We don't need to scrap too much.
the idea. So
Roberto, you've got a gate to replace Go.
That's packed.
and his argument, one other argument that he has is a little ugly picture, but one of the arguments is that when they construct, this is a queen where the bees construct for the queen to stay. If they construct just a place for the queen to stay, it's completely asymmetric, it doesn't have any shape. And what he says is, where is the gene telling the bee to construct something that is pretty now? If just one bee constructs instead of a bunch of them, the thing is completely ugly. So he used that to say the bee doesn't have an idea of geometry or making something that is symmetric. When they all work together, it works out it's hexagonal because physics makes that. But, so the point is, today, modern view, who wins from those two views? And before I talk about like what people have said who wins of those two dudes, not that they really care, but I'm going to talk a little about some other things. I'm going to come back to that in the end. But in both ways, both the ideas that Darwin expressed and the ideas that Thomson observed, they all come with this idea that in 2D, if you try to divide the space into regions of equal area, hexagonal is the best. And that was a conjecture from 1800 BC, and it was still a conjecture. Cannot be proven, mathematically. And turns out that it can. You probably were here still in the time that Tom Hales was your professor here. And this is one email that he sent to one of the editors of one journal that also writes a book about packing, where he says, if everything goes well, I announce a solution for the honeycomb conjecture in a few days. I don't make any assumptions and everything. And he says, given it's a celebrated, problem, I think you'll be interested in publishing that. And of course, he was a professor here at the University of Michigan while he did that. And he also says, of course, I'm fascinated by the Kelvin problem too. So Hales solved the problem that if you try to divide the space into regions of equal area, hexagonal arrangement is the best. And when he says, I'm also interested in the Kelvin conjecture too, is the Kelvin conjecture is kind of the 3D version of this problem. If you take the space and you try to divide in regions of equal volume, like those bubbles, imagine that you could make all those bubbles in the same size. What shape would those bubbles be? Because the bubbles are trying to minimize the surface area that they can form. So his question was, what is the shape that can fill 3D space with a minimal equal area? And he proposes that this is the shape, is another conjecture. And a similar conjecture was also proposed by Kepler, by saying if you take a bunch of spheres and you try to pack them together the best you can, the FCC arrangement between the face-centered cubic, or the way that you stack oranges in the supermarket, that's the best way of stacking spheres. That was the so-called Kepler's conjecture. And although Hales worked in those two problems that were open since forever, he actually solved the second problem, the Kepler conjecture. I'm going to talk. He made a proof for that. But before that, Kelvin's conjecture was found a few years ago, 10 years ago, was found to be wrong. If you have actually in a unit cell of 16 particles, not only this that I showed before, it can be slightly better than Kelvin's proposed structure. Kelvin only had one building block, one shape that could tire space. This is actually composed by 16 particles, and is, I think, 1 to 2% better than Kelvin's idea. But Hale is still working here in the University of Michigan, made a proof that the stack of oranges that we see in the market are the best ways of packing spheres together. It was fun because it appeared in newspapers and things. He said he was surprised because math doesn't come to newspapers very often. But it was fun that the way he did was, I cannot prove that this is the best, but I think I can prove everything else is wrong. So he just decided to devise like a program, an algorithm, to divide how many ways I can put spheres together to pack in a space, and then I'm going to prove that every single possible way is wrong. And it turns out that he made these using like 250 pages of math and a program that like outputs 3 gigabytes of data saying everything else is wrong. And he tried to publish that, and the guys at magazine said, okay, we can publish that, but we are going to cite 12 referees to that to look at all of your data, and they are going to look at it. And it took them 4 years to come together and say, we are 99% sure that this proof is correct. We cannot go and say that this is correct. And this was also very controversial because it is using a computer to make, to prove a mathematical problem. It is not very usual. Instead of just going and making the solution by hand. It was also done here. But what about other shapes? If you think about spheres, it was already this big problem on how spheres pack. How do they come together? But there are many, many other shapes that you can think of, and how can you pack them? How can you put them together in order to get the maximum feeling? This has importance, for instance, for the case of M&Ms. If they want to, pack as much M&Ms as they want in a box, and also, here you have chocolate and things. They have those shapes just because it's easier for them to ship them and save some money on that. One example that we have from packing is the work of Paul Chaikin. I just mentioned before. This is just one example of things that they do. Yes, just for better packing, they can change the shape of a watermelon just to shape them better. And this is the work I was telling that Paul Chaikin in Princeton University with Salvatore Torquato, they studied the packing of M&Ms, and this gave him M&Ms like for life. They gave him, and his idea was another conjecture. I hope I'm not making that too confusing, but there is a Ulam conjecture that says if you take spheres and you try to pack them, those are the worst shapes. Anything that is convex that you can think of, if you put them together, they are going to pack more space than spheres. The spheres are the worst of all. And they thought they had found that M&Ms actually were worst, and then in computer simulation, they made an experiment and found no, ellipsoids are also better than spheres. But I'm going to talk about tetrahedra today. That is the simplest Platonic solid can imagine. It's just those 4 faces made out of triangles that are all in the same size. And already, in 300 BC, Aristotle said tetrahedral fill space. You can put them together and can completely fill space. And it took 1400 years to come Miller and say, no, they don't. Who are you, dumb? You cannot take a tetrahedra and put them together in fill space. You're going to see that if you start playing with tetrahedra, I think I have some here in my bag. I always carry tetrahedra with me in my bag. You never know when you're going to need them. But if you start putting tetrahedra together, you see that you need to put glue between them. You have those gaps, and if you start putting them together, you see that those gaps start opening more and more and more and more, and you're going to see that there is just no way of filling space because those guys, they don't form anything that can fill space. So in 1400, Miller said that, and in 1900, Hilbert has this famous list of problems that are important problems in physics, and he said, add that problem to my list because it has been 1900 years. And no one has found anything. Put that, it's an important problem, put it in my list. Minkowski came with a solution, analytical solution. It's actually pretty low, 9/38. It's like if they packed very loosely. If he had played RPG and had played with some dice, he would see that he could, pack them better than that. just by doing some experiment. But he was a mathematician, no experiments allowed. Those two guys reported very similar times, better packing. Until 2000, that was pretty much what we knew about tetrahedral, the packing of tetrahedral. That's what was out there. Until here in 2006, Torquato, the guy I showed in the previous picture, and Conway, mathematician also in Princeton, they came with this packing of 74%. They say, well, we made a computer program, put one tetrahedral to move around the computer program and interact with the others and try to find the maximum packing, found 74%. And in 1st of January 2007, Beth Chen, who is a mathematician here, came with this better packing of 77% with those tetrahedra. And it didn't take long for Amir, who was also here in University of Michigan, but working with Sharon in the chemical engineering department, working a completely different problem, but also looking at tetrahedra, found a better packing of 78%. And again, it also didn't take long for Torquato to get a similar packing. And then Amir decided to try to compress his box as much as he could. He got 85%. And then after that, Carlos published a paper saying, I found a packing that's even better, it's 47. And Torquato said, oh, no, actually 85 is the best. And then in the end, Beth and Sharon and Michael, they stopped and looked at all that was going on and said, oh, there is a function that seems to be converging here. And they made the solution for the conversion of the problem that found as being 8563, and still today is the best packing that we know for tetrahedra. So that's where we are, right? In the end of 2009, that was the best way of packing tetrahedra together. So again, why is that important? Why? It came to the New York Times because it's such a simple problem. If you take tetrahedra and try to put them together, what's the best way of solving this problem? It was the first big news of the new century in January 4th of 2010. It was for a week the news of this, the century, and but the reason why we were interested in that is that people can make colloidal particles. So those are nanoparticles, micrometer particles. And those nanoparticles that people are interested to make chemical compounds, now they have different shapes. Usually, it used to be that people could make colloidal spheres, things like that. But today they can glue spheres together and make polyhedra out of spheres. They can make things with different shapes, like cubes, like those prisms. And they don't know what is going to happen if you put those colloids together, what kind of structure is going to form. We already know that if they are spherical, they're going to form the orange stack that they showed before. But if they have other shapes, we don't know. And that's why we were studying tetrahedra. And what we found was that if we put a bunch of tetrahedra in a box, here's a bunch of tetrahedra, and we shake this box, and here I'm compressing this box and trying to see what it forms from that. The color here doesn't matter, it's just to show that there are different polyhedra. And basically what we are doing in the experiment is we have a computational experiment, computer experiment, where you're shaking this box and compressing, trying to compress more and more and more. And you can see that it starts, if you believe me, starts to form layers here. Those things start to organize and form layers. It turns out that if you cut in one of those layers and look from the top, that is what you see. And it's kind of hard to see that there is actually a pattern here. It's a quasi-crystalline pattern. And those guys, they do not attract each other. You're just compressing. And they form a crystal just due to entropy. The first two things that you can think is, wait. You're saying that the entropy is making those guys to order? That's weird. And the second is like, what the hell is this thing? Is that, So we're going to just make a brief parenthesis here to talk about entropy. And when Boltzmann came with this equation to say that entropy is S log W log K, is basically he was saying that in order to maximize entropy, you are maximizing the number of ways that a system can be according to a given thermodynamics parameters, so temperature, pressure, or something. So if you have all the air molecules that are here in the air, they can all be in this corner, but they are not going to be because there are way more ways of them to be arranged in space here than being all in this corner. So entropy, we used to think as entropy as being a concept associated with disorder, but entropy is actually related to the number of ways, as I said, of number of options, ways that you can put things together. And this is an important concept that usually we can get it wrong because there are very few cases where entropy actually can order, but here's one of them. And as an example, I'm going to show those two things here. Imagine you have a system full of pencils, you just shaking them, and the color here means they are becoming green if they are ordered in the same orientation. So if you take a pencil and you look in the others around it, and if they have the same orientation, you color them green. Otherwise, they are red. And you see that if you start to compress, they start to order in some way. And the idea here is that if they order, they have more space. It's easy to think that if you have those pencils oriented in the same way and you compress, they have more ways of being like that than being completely disordered. Disordered, they are going to just get stuck in one position and they cannot move. The same thing also happens for spheres. What is not as straightforward as for pencils, you can imagine that they cannot move. But if you have spheres and you compress your system, again, they start to order. And here is not the orientation, but I'm measuring if they are locally forming crystals. If everyone is hexagonal, if everyone here starts to exactly to stack like the oranges, I color them green. In the same way, I'm just compressing the system, you'll see that they start to order. And the basic idea is that if they order and they form these, they can move around and they can jiggle, and that means that there are several ways of these particles to be in this configuration. If they get stuck like that, probably this particle can move around, but all those particles cannot move around because they are just stuck in a glass. So if you calculate the entropy, the number of ways you can have the system in some orientation or position, this is the maximum entropy that you can find. So entropy can order systems. So can come back to, this is a crystal. I can come back to the system of tetrahedra. Those are some tetrahedra like those that I'm showing. And what you see is that they start to form those rings and they start to grow. Instead of a crystal where everyone is periodic and it's just a copy of everyone, you just take a translation of a unit cell. Here you don't have a unit cell. They start growing like radially. And you cannot find something that you can just copy from one side to the other and it's going to be the same thing. And that is pretty much the idea of the quasicrystal. What I was saying here, basically if you have a crystal, you have particles that are forming on one unit cell that you just repeat it over and over and make a whole crystal. And the way usually you do, if you have atoms, you make a X-ray diffraction and make a neutron scattering. And you look, and if you see those spots here forming a square, it basically means that your structure is cubic. You have those squares everywhere. But if you try to do that in 2 dimensions, as I mentioned before in the honeycomb, you have those squares, triangles, hexagons. If you try to tie your space with pentagons, you're going to see that you start to have problems. You start to have those gaps that I was talking about. You cannot fill space. You have those gaps. But one thing that you can do, and this was found by Penrose, was that you can take pentagons together and combine them and make a bigger pentagon. Now you can imagine these as your new pentagon and combine them together with other pentagons, and you have now a bigger pentagon. And you can keep doing that and growing. And this he did, but only for like aesthetics purpose. He did, and he found it pretty cool. And he has several of those drawings where he finds nice structures that you can make with pentagons. But he never thought that this could actually be found in nature. And one of the nice things is the whole thing, if you keep growing, is another example. Is basically here you have pentagons, now you're going to have these stars that are needed in order to make this thing to fill space. And you can see that it's not like a crystal. This thing here is not just a copy of this. You cannot just move around and it's going to be an exact copy. So this thing was found to actually, in nature, like atoms to form this thing. Here's an example by Chapman, who found a quasicrystal in nature. And here's like his logbook. And when he made experiments in diffraction. And when he found those 10 folds, this thing here with 10 peaks, he said that can't be right. You are not. If you have a crystal and look at this diffraction pattern, you're never going to find 10 because 10 cannot fill space. I'm wrong, and he made the experiments over and over and over again, and he found the same thing. So he published it. And basically what happened, what he describes after that was that he was fighting for the truth. Like everyone else was just saying, you don't even know how to make your own experiments. You should just change to do something else. You should stop doing physics. And the problem was that one of the biggest guys that would just everywhere.
Oh boy!
Yeah, it was just Linus Pauling, who is the only guy to have 2 Nobel Prizes alone. And he used to say there are no such thing as quasi-crystals, only quasi-scientists. And it was pretty hard for him, but luckily in 2011 he won the Nobel Prize for this discovery, because now we know that all of this is actually true. Here's some examples of quasi-crystals in nature. We have those. You see that if you have a salt, the common salt, it grows as a cube, exactly because the symmetry is cubic. Here, the symmetry is like icosahedral, it grows like a icosahedral kind of thing. It's an example. And I'm going here back and forth, but just to say that the reason why we were studying those geometries, those things, is again because people can make colloidal particles that have shape, and you're interested in understanding what can you do with those shapes, what kind of structure can you make. And if the colloids were spheres, all that you could do was a stack of orange in the market. But if they have different shapes, you can do different things. So then is finally when I come in the story, but just I'm going to talk briefly about what I do in the work in this whole part. And what I started doing when I joined the group was, if you take a tetrahedron and start to make different shapes out of a tetrahedron, what is the packing? How can you pack those tetrahedra? What's the densest packing that you can get? Not going to explain exactly how we do that, but basically you put them in a box and you shake and you compress and you analyze what you can get. And here I make a complete family of tetrahedra, and if you truncate their corners, you can keep truncating until, kind of surprisingly, you end up with an octahedron. And I calculated the densest packing of all of those guys. Those were known. Here was known, the packing of tetrahedra, just told you guys about that. As I kept truncating, I found a new shape that is able to completely fill space. They have books in math where they have like a whole list of polyhedra that can fill space, and this one wasn't the list. So it's the, I don't know, Damasceno polyhedra? So important that you can. And also this polyhedra is important because people have, in studying this particular one, is Archimedean polyhedra, and people have found packing, and found that actually the densest packing can be found. But what we are really interested in, what if you put them, like tons of them, in a box, and you try to compress them, and start compressing them, and leave them to find, via entropy, what's the best way that they can organize in a given pressure. And this is different from densest packing, because here the particles are really, literally how, in the exact same way as if you have this box and you're just shaking this box full of M&Ms and you try to see what's the best arrangement that they can be. Not always, and usually what we found actually is that usually they do not correspond to the same thing as densest packing. If you just try 1,000 particles in a box and try to compress, this is not what you're going to find in experiments. And we found that as you truncate, you get the quasi-crystal that was found before. And for some specific other polyhedra, you can find like a diamond lattice, exactly like a crystal that you find in diamond, you can find with polyhedra and other structures. So here's just some examples of these. Using tetrahedra making this quasi-crystal, truncated tetrahedra making a diamond, making another phase that is complex, has 16 particles in the unit cell. This thing that repeats everywhere has 16 particles over there. And if you have octahedra, they form a BCC structure. So what it seemed was like tetrahedra was just the tip of the iceberg for all of this. Like this shape seemed to maybe open the possibilities to get all sorts of crystals from, just by changing the shape of the particle. So last summer, I spent some time playing around with some more shapes. Those are basically all the Platonic solids, all the Archimedean solids, the Catalan, all the Johnson solids. It's pretty much all the symmetric polyhedra that are cataloged. And I studied them all. And here are some structures. We just found, as expected, we just found that all sorts of crystallographic structures are found from those polyhedra just because of their shapes. just some system, even hierarchical kind of things. You have pyramids like that. They can come together, they can make a cube, and then the cubes come together and make a cubic lattice. It's an example. And again, there is no attraction. It's just a bunch of particles hard that you put in a box and you're shaking and compressing. So I separated them in classes, which kind of shape makes what, and then start to think, why are those guys making these, why are those guys making that? And we came up with kind of a theory on just by looking at the particle, you can measure, basically what I'm doing is you measure how spherical the particle is. And there are several ways of measuring, but we found one that's particularly good, that is just measuring the ratio between area and volume. And if they are very spherical, this guy goes to 1, everyone behaves like spheres. They pack like the oranges in the market. And as you start to make faces, the faces start to be important for them to come together, and they start making other structures. So those blue, it seems like they behave like spheres. That's what it means. The green one means that they form crystals, different kind of crystals. The orange ones here, they never formed anything. We found what we call a glass because of lack of order. You couldn't find any order. And if they are like coins, or if they are very elongated, they form what we call liquid crystals, where they have a specific orientation. Like imagine a bunch of coins that all stack to each other, but they are not exactly a crystal because they have no translational periodicity. They are not copied, but they all point in the same direction. So this is basically a theory, but I'm just going, in a very quick overview of what the direction of the work was. And the main point here is that if people can make shapes that are now different in the colloidal scale, we can think about using them as Lego to build a specific structure that you want for some property, mechanical or optical or anything, and start constructing this way. At this point, I imagine that you guys would be either sleeping or just angry because I didn't talk about the honeycomb and I didn't talk about the answer of the problem that I was talking in the beginning. But this actually is very smart. Could it work, Professor? From there. I've read some books before, but yesterday I made even more research, and the answer is that there are no answer. There is no answer. Is that people still don't know actually if as far as I could find, if the Darwin's way of thinking that the honeycomb is made by some way of gene expression that was passed, saying hexagonal is the best, or actually if the amount of bees together came in order than in a hexagonal pattern. But then I found this interesting example of wasps. And sometimes just one wasp can come and they make their own houses. So in this case, at least, the wasp is by himself. So there is no such a thing as several of them constructed things that are coming together and making a hexagonal pattern. So last night, pretty much, I found this as a counterexample for Thomson's idea that is formed because a bunch of them are coming together and making this pressure. But at the same time, I kind of thought in something that makes much more sense for me, is that if a wasp comes here and makes a cylinder surrounding it, and make one cylinder, and then it decides, oh, I need more, and then it decides to make other cylinders. If you're making a cylinder around, you already use this wall, and you construct another cylinder using this wall. And then you come here, and you make another, like let's say you're just surrounding this one, you make another cylinder here using this wall, and now you have to use also this wall. You are saving material. There is already 2 walls here, I just make the rest of my cylinder. Here I come, and even if you go to 20, 30, 40% of the difference between one cylinder and the other, you cannot fill anything more or less than 6 around this. Because in order to fill 7, this one would have to be a half of this size. You have to make 2. So it's like you start to make cylinders surrounding one and using the walls that you already had. And what happens in the end is that instead of having a cylinder here, you're going to have a hexagon, just because you have 6 neighbors and you use it all of the walls. So that seems to be much more, I don't know, simple or appropriate, kind of using Thomson's idea. That's basically one of, I don't know how much that can be used by the bees, the same example, but at least for this one, it seems to make much more sense. So that's pretty much what I had to tell. The works were done with my advisor, Sharon Glotzer. Michael is a postdoc, some of the things about packing I said were done by Beth Chen, a mathematician that's now in our group, and Amir, who's now doing a postdoc in Princeton. And those are some fun books to read. Darcy Thompson's, although it's like a 1,000-page book, but it's pretty interesting. Philip Paul has a book on just patterns. He talks about patterns in nature. And there is this book about packing that's also pretty interesting. And Jeff West talks in YouTube.
So if you go back a slide, and on the rightmost picture, the top compartment, it looks like it's kind of there's a curvature along, like around all the edges that aren't bound to the other
like
existing faces. Right? Yeah. Right. So that would indicate that it's a structural component and not a biological component. That is to say, the wasp isn't creating the walls, but rather just the pull of the creation of the new compartment creates the structure. So I mean,
that's what sounds more likely, right? And you don't have to think that they somehow know that these feels more things. They are making what they can.
But I mean, just structurally, it's not a hexagon yet.
Exactly. This one is structurally not. But as soon as if you make 6 neighbors with the walls touching, it's going to become a hexagon.
So actually, in the other picture earlier on in the talk, when you were talking about honeycombs, I think the one where you showed the house of the queen.
Yes.
It's very clear. Like there's the ones at the edge is completely spherical, and the ones in the center are.
This picture is ugly. I didn't look at it very much because I kind of.
So you see the one at the top.
This.
The ones, yeah.
Those
so these
very
ones are very
spherical,
spherical, whereas the ones further in are.
Yeah. So. He's one of the things that Thompson says is that they construct kind of randomly spheres, and as this thing dries out, materials go, this thing opens more and more materials go here and make these kind of walls. And as soon as they are almost touching each other, it forms a hexagon.
But you see this in cells, you see this in foams.
Right. But it's so I couldn't find. There are still lots of. So one of the things, actually, I read, one of the books that I read says explicitly that Thompson is wrong because they found out that, I have a better picture here, I think. Here. You see that the honey is kind of coming in this direction? So it seems like the bees, they always create like a 7 or degrees kind of thing that makes sure that the honey is not going to drip, So it says if bees are able to make this 7 degrees curvature in every single honeycomb, they are able to make hexagons. But I think that if they made a honeycomb that was in the vertical, the honey would be just dripping down. I think they're smart enough to just say, well, that's not working. Putting honey here is coming down. Putting honey here is coming down. So I don't see this complete, thing that because they make this 7 degrees angle, they are smart enough to make hexagons.
Isn't the 7-degree angle? Sorry. Isn't the 7-degree angle also related to like viscosity and gravity, or?
What they say is that they found that bee has a notion of a gravity field, and they use that to exactly create something that is 7 degrees always to the horizontal.
I was just going to say, I feel like biology probably could figure out a way to make a hexagon if that were the constraint of the problem, but they don't need to make a hexagon. If they don't need to make a hexagon, why would they? So I don't think it's just because they can make a 7-degree angle doesn't mean they are making hexagons.
I think the big controversy is this thing that it says biology always follow physics, so you can predict things. You can say you never. But the predictions that we have right now is pretty useless. I can predict that you're never going to find a goat with a P as his horn, like writing my name, because it's not physical. But okay, so it's a useless prediction. So, but this is, I think, is the way, Professor, that Jeff West works in this direction, that predictability, right, of biology.
Yeah, the whole scaling thing that they do is very much towards that end. It seems to be a critical point here that you have various levels. Each level puts constraints on the next level, but it doesn't determine the next level.
Right.
So if I know the valences of atoms, that says that I can't form inorganic, say, molecules that go against the valences. But knowing the valences doesn't tell me what all the forms are that I could get. And I think it's very important. This is not a question of right or wrong. It's a question of what level you're trying to develop the description. In some sense, they're both right. But you really got to pay attention to how one level affects the next.
Yeah, and you need all the constraints to understand the problem. So, for example, about the horns, like it seems because it sounded like there's this big fight between the two theories. But to me, it seems like biology could tell you that you're in this island, so you need to have horns that are longer or stronger or whatever because the weather and the other animals and whatever biology says, and also, depending on your biology, you can create horns that are made, depending on what you eat and what your body produces, you can make them of this material, right? Or this combination of materials. And then physics tells you, okay, given this material that you're genetically tuned to have in your body, and the fact that you want two horns, then, you are going to bend in this way. They're going to bend in this way, right? Because of
what
laws
we
of
find
physics.
from physics professors actually that you can, or in theory at least, you can predict if you know everything about because we're talking about classical physics, not quantum physics here, in terms of those objects. If you know the shape of the object, you have all the information that you are needed to know what's the best packing or what's the result of them coming together, what is entropy going to do. In theory, we are supposed to predict what is going to come just by looking at the specific building blocks. You look at the polyhedra I showed, that's what I've been trying to do is, can I just look at the polyhedra and take measurements from it and tell you what is going to form? And it seems like you can, just because all the information it's there.
Yeah, the thing I'm cautious about, so I give you a box full of Legos, and I ask you, what structures can you form from that box full? And, knowing what the Legos are, I've got all my generators, but I don't know what the possible, they're so big that I need some law one level up to help me say what's possible,
so
some constraint.
Yeah, exactly. So what we do actually is, when I say that I know what is going to form in specific constraints of temperature, pressure, if you put in this temperature, if you put in this pressure, the thing that minimizes energy is this one.
Yeah,
so
that's a good case in point, because temperature is an emergent thing from the next level below. It's not, you can't really reasonably talk about the temperature of a single molecule.
Yeah. It's only when you put them together.
Yeah, so you get PDT and stuff like that. I don't know, I saw maybe you there. Anyhow, a week ago we had a complexity seminar by Jane Wong from Cornell. And she took the flight of dragonflies clear from fluid flow, from the Navier-Stokes equation, all up to the level at which they change direction and so forth and so on. So she worked at about 3 different levels with constraints at each level. And it's just interesting because not many people do that. Not many people go all the way. And it was fascinating. Just to give one example, which I never would have thought of, is dragonflies in effect have a torsion spring because the rate of flapping and so on is such that they have to get some kind of anticipation in order to turn it. As you mostly know, dragonflies are hunters. They catch mosquitoes on the fly, so they got to be very, very good. And so what they do is they sort of do this torsion straight, they put the torsion on it, and then suddenly, they're off in a new direction. Just stuff like that. It's just fascinating to me. By the way, I should mention, Darcy Thompson's book is a big book, but there are lots of pictures.
That's true. That's true. And it's fun to read.
Yeah.
I have more questions.
Yeah, I've got two actually about the materials that you were creating. So first off, do you know any of the material properties of these guys? Or?
So the whole grail here is we're trying to make computers where instead of electrons passing light, we can use, right? So the point is you want to make a structure for which you send a beam of light and the light goes straight following a path. So we want to have materials that are what we call have a photonic band gap, materials where the light doesn't go through the material and just follow a specific route. So there are some of those things, and the diamond that I showed before, if you take a bunch of spheres and you put them in a diamond configuration, that has this property. But every time you take spheres and put them together, they want to form the FCC, the one of the oranges. They don't want to form a diamond. So one possibility is using something that is not a sphere, using the tetrahedron as a show.
Are you able to so-called self-assemble three-dimensional photonic crystals? Is that using the jargon? Would that be?
That's the direction. There are two main problems. The main problem is that people are just starting to make shapes that are not spherical. And from some years ago, people were like, why am I going to try to do that? And here's why. It's because you can get some structure. So now we are like motivating experimentalists to make specific polyhedra things. So no, people haven't done any self-assembly of a structure that has photonic properties.
And the second question is just a quick one, but when we were looking at the system and it was maximizing entropy, essentially, if we were to look locally at one of the ellipses, I would say, the system itself has more possibilities, more combinations. So I imagine each local point also does, but it's not the same set as it was before, because previously it seems like it's just jiggling roughly in one axis. So I'm wondering, once the system was evolving, certain parts were turning green as if they were crystallizing. Is that somehow expediting the process, or is that restricting the?
If I get that correctly, but if you take the particles and you leave, if it's loose, it's assisting like 40% of packet fraction, means that everyone can move around very nicely, and that's where I start my simulation. Everyone is happy as it is. They are not going to form an ordered thing because everyone can move around. But imagine that you compress the system and leave everyone very, remember that the example I used in class, like everyone is caged, and it's like people dancing in a party, and everywhere that they go, they bump into other people, and they cannot dance. And then people decide to just join with the guys that are around, said, oh, let's dance everyone together here. And they start to dance everyone together, and said, oh, if we dance together, we just bump into each other. So only if you apply pressure, only if you put this constraint that you have a lot of pressure, then it's better for them. It has more entropy to be ordered, just because they are going to bump less.
Is it possible for them to minimally have less possibilities? Let's say overall the system has more possibilities? Because it seems like each of them are just moving about.
Right, but the point is that if I just take the system and compress, probably if you get to the stage where it's a glass, you can cage everyone, and everyone is. The problem is that you have to compare what you have and what you could have, and it's like the possibility that you have now that is ordered. Everyone has more movement than everyone else, every other possibility. So one case is, I think that's what you're asking, but if you have one thing that is like one system with a gas and everyone is here.
The variance goes down, but the average goes up.
Yeah, if everyone here is caged, but this guy is free, you have several configurations because this guy can move. But now imagine that everyone is actually free, but just a little free, right? You have 6 guys here. You have something like that. For sure, this one had lots of more space, but if you calculate the probability that goes with the number of configurations, you have to take the... Now, here you have one guy with many possibilities. Here you have 6 guys with some little possibilities, and this means that the number of ways of the last one is way more. There are way more ways of putting those 6 to move just a little in one moving along. That's it.
I think we might be out of time soon.
We have the other talk.
Okay, so one last question. I was going to say, like, this debate exists in biology. If you read, like, Stephen Gould and his talk about spandrels, it's a really classic paper, and isn't the adaptation versus just developmental constraints.
It's still new, like.
Oh, it's very
recent.
old, very, very old.
No.
I see. Yeah, that's it.
Right. It's a really great paper. You should read it. It's all about spandrels don't exist because they are adaptive. It's just because that's the constraint of the building.
What's the paper?
I don't think it's
What's the paper? Is it a book or a paper?
Stephen Gould's paper.
It's in his books too.
On
so
spandrels.
yeah.
A spandrel
are
is
a packet you constraint
too. It's when you
Yeah.
have an architectural building and then you have arches. The space between the arches is a spandrel.
Okay.
but you don't create the spandrel. It just is part of the building. And so they talk about this a lot. And I don't think in biology people necessarily think everything is adaptive.
I think it's important to not think of these things as either-or kinds of things. That's where often these things, for some reason, get into the battles. You know, Gould talks about punctuated equilibrium, for instance. And, you know, there are aspects of that, but it's not, is there always punctuated equilibrium, or is there gradual change? A misinterpretation, by the way, of what Darwin says. He doesn't say that at all. But the point is, these are not things that have to be either or. It's what proportion of the explanation comes from this direction. Or so I claim.
Okay.
Okay, let's